Welcome to Bookwrights House, where we explore the minds behind works that shape intellectual inquiry and deepen our understanding of the world. Today, we turn to the elegant and rigorous world of geometry. Our guest is Franz Rothe, mathematician, educator, and author of a comprehensive multi volume work that grew out of more than a decade of teaching fundamentals of geometry. Built from extensive lecture notes, carefully crafted exercises, and hundreds of computer generated diagrams, this monumental project bridges classical Euclidean foundations and the vast landscapes of hyperbolic and differential geometry. Good afternoon, everyone. My name is Elijah Barcelona, and Mr. Rote, welcome to Bookwrights House. It is a privilege to have you with us. Okay, so first, let's talk about the foundations and writing philosophy. So, user-friendly mathematical writing, your manuscript is substantial in scope and depth. So, what deliberate choices did you make to ensure that such rigorous material remained accessible and user-friendly for students?
Well, I begin with the basic Euclidean geometry, but I don't follow the curriculum of school. For me, the axiomatic viewpoint of Hilbert is in the end more important than the history. Nevertheless, I have subdivided into 6 volumes, and in the second volume I start rather in a more pedagogical way, nearer to the kids before going to this more axiomatic view. And there I start the second volume with a Thales theorem. There is a right angle which one puts in this semicircle. And that is really a famous theorem because it was really here that the notion of proof and exact proof, not only empirical facts, but exact proofs were introduced in geometry. And in antiquity, that was then had a very good achievement, really a marvelous genius work of Euclid's Elements. Yeah. That is, so to speak, the Old Testament of geometry. And the New Testament of geometry is Hilbert's work, Foundation of Geometry, which is from 1899, and where he introduced axioms which then can realize geometry even without vision, just from axioms. And he introduced the 5 groups of axioms: the axioms of incidence, of order, of congruence, the parallel axiom, and the axioms of continuity. And then the theoretical investigation needs to begin by building the theorems at first, the more general, nearly ridiculous, simple geometries which are based only on part of this axiom system. Then in the course one comes to the so-called neutral geometry, where one can already discuss triangle congruences, but one does not introduce whether the parallel axiom is true or false. It is just the theorems which hold in both cases. And that neutral geometry is really dealt with in all details in the first volume of my 6-volume work. That is the volume here, axiomatic and neutral geometry. Yeah. But as you can see, there only very simple things happen here. For example, in this system, you have already the theorem that the base angles of an isosceles triangles are congruent. But otherwise, that gets partly too abstract for a work which I want to be able and willing to introduce for a teaching of many courses. There, the second volume, the basic Euclidean geometry, is much better. Here, I begin, as I already told you, in a more simple way, I discuss there the theorem of Thales and the basic Euclidean constructions, which is like dropping a perpendicular is very popular, happens all the time. Then erecting a perpendicular, the isosceles triangle again, and again, then the angles put in a circle, which are nowadays in school not so more very taught in all details, but it's all in this book also. And then, yeah, the first part is really not stressing all this axiomatics so far, but then in the middle I go to a section where I talk really that I take this axiomatic view serious and about Hilbert's work there. And in the third part I use then the parallel axiom also and introduce all what comes in school with 8th, 9th grade and so on. That means the trigonometry, the Pythagorean theorem, and the measurements of areas and the relations of angles and segments, and what you have most seen in school, and what is a bit the harder part of geometry. That is in the final part of this second volume. And that course is based on my teaching that course fundamental of geometries for more than 10 years at the University of North Carolina at Charlotte. Yeah.
So, in your hyperbolic geometry treatise, you transition from classical Euclidean construction to models such as a Poincare disk and the upper half plane. So,
Yes.
how did you determine which model should serve as the primary conceptual anchor for students? Did certain theorems translate more naturally in one model than another?
Yes, these are the questions. We don't talk about hyperbolic geometry in school because
Mhm.
you see, even the most famous theorem, the Pythagorean, has a totally different form. There is not just a squared plus b squared is c squared, but it is cosine hyperbolic a times cosine hyperbolic b is cosine hyperbolic c suddenly. So you see, you talk of a different world. Now, is this world fantasy or is it reality? That is not the main question here. The main question is whether it's a logical, consistent world. And that is true because you can use as axioms, there again, Hilbert's axiom system, plus instead of a unique parallel to a line through a point, you have the so-called asymptotic parallels to both sides. That is very important here. And now, to build then hyperbolic geometry on this, in this way, on Hilbert's system is possible and is done in the later part of my volume 5 here, really
Okay.
also.
Yeah.
Yeah, this is really there. But this is an approach which needs the willingness to to go through many axiomatic things and build again, um, and is not at all in any way visual. Yeah. Because you have just, instead of the unique parallel, you have the asymptotic parallel rays. You have a line and a point not on a line, and you go from this point not on a line and to draw rays which just barely approach to the line on either the right or left end and not intersected. These are the so-called asymptotic parallel rays. Of course, in Euclidean geometry, they will together make the parallel, the unique parallel.
Yes.
But in hyperbolic geometry, those parallel rays form an acute angle. That is very surprising. and was already discussed and discovered by Gauss and Lobachevsky in a very abstract way. Um, and then later on, Poincaré had another approach to hyperbolic geometry, which is really visual, but to the price that one needs to work with models. And in this visual approach, one has, again, drawings which look like complicated things in
Yes.
Euclidean geometry,
Mhm.
like here this. But the Euclidean plane is here used in a very strange way. One puts a circle once forever in the plane and says now the points of the hyperbolic world are the points inside that circle. How can this be? The idea how Poincaré explains it is then while measuring, there is kind of different temperatures in this disk. And if you have a measurement rod, if you go to the boundary of this circle, then the rod shrinks, and therefore you can never really, by measuring inside, go over the edge of this circle.
Check.
That's the basic idea. So there's a new metric, and that has the effect also that the straight lines don't look straight in the usual Euclidean sense, but the straight lines are circles which intersect the boundary circle in right angles. That is a very strange but very fruitful idea there. So you can see this explained and then base the constructions on this in this volume. So I go with Poincaré's disk model as the first thing to go with, and that is good in the sense that you can do something really, but what you do has always two different ways to look at it. Here is, for example, explained how one can then really draw a line between 2 points. But it is very strange. Then the line between these 2 points is really a circular segment which is perpendicular to the boundary circle. And that is not a contradiction, because one needs now to really distinguish always two things: the underlying Euclidean plane and the hyperbolic world built axiomatic in it. Yeah, that one does not learn so directly in school. But something similar happens in school with analytic geometry. There you have numbers and pairs of numbers, which are the x and y coordinate, and you have the Euclidean plane. These are two different notions. On one sense, the points are just the points in the plane. In the other sense, they are pairs of the coordinates. Now, these two things needs then to dealt with in a different way. If you think of pairs of coordinates, then you get for the line between 2 points a line through 2 points with the given coordinates, which you learn in school also as an equation of a line through 2 points. Yeah, and that there also you see you need to make the straight line out of the notions which are used in the model. In the coordinate geometry model, these are just these pairs of numbers. And in a bit similar way, but differently, but mentally also, it's such a construction here from Poincaré that you have for the line between 2 points, you have to go inside that circular disk and then find the segment which is perpendicular to the second, which is perpendicular to the boundary circle. And that gives then also the shortest distance if one measures distance in this strange way mentioned earlier. So this is somehow the very basic idea. Yeah. And in this way, popularized by Poincaré, the famous mathematician Poincaré, and also by the German mathematician Felix Klein. In this way, one gets another way to think about hyperbolic geometry and get many theorems in it. With some theorems are the same because they are part of neutral geometry, and other theorems, they are totally different in hyperbolic and in Euclidean geometry.
Okay. Okay, so when students later encounter non-Euclidean structures, which axioms prove most conceptually challenging? So how did it shape your exercise design in volume 2?
Well, the axioms try to depict the natural intuitions about Euclidean geometry. But if you alter the parallel axiom, you get already a system which allows also, with the asymptotic rays, hyperbolic geometry, which is very surprising. And so you see, the axioms can be used in different mathematical contexts or theories or models, how you call it. And that is really quite interesting. And this will be used really very much. So to make geometry just from axioms and proofs and theorems is of course very difficult. You want to have some intuition, and therefore you have this what is called models, what is called also examples, what is happening in analytic geometry, which is happening in this Poincaré and Klein's model for the hyperbolic geometry. And then you get visual helps with the advantage that you get some intuition what theorems are true, but with the disadvantages that you can get confused about the complications. Yeah. And then one begins to be in a mathematical system where one needs really to find just paths and follow the teacher along some paths which have been turned out to be useful over many generations. Yeah, that is really. So one surprise here, which many of the difficulties of this kind were already foreseen in Euclidean's work. And one is this so-called principle of superposition. Yeah. So usually we think of rigid geometric figures like rigid bodies in physics. Yeah. So a measurement rod you can transport from one place to another and its length does not change. Yeah. And an angle also you can measure with some simple devices also, and you can transport it from one point to another. And that is part of the natural intuition. But it is used not in Euclid very much, only to prove the side angle side axiom for triangles it is used. And it is not used at all in Hilbert's axiom system. There, the side angle side congruence can be proved from the axioms, but the axioms allow not just transport of triangles from one place to another, but just transport of segments and transport of angles in a restricted way. So the system of Hilbert is different from the Euclidean worlds there. Yeah, that is really makes it has the advantage that one can use it for hyperbolic and Euclidean geometry, but the disadvantage that the natural way to deal with angles and segments is not so directly present as it is used from building and architecture and all that.
So let's talk about projective geometry. So projective geometry as a bridge, projective geometry appears early in your first volume and returns later in connection with hyperbolic geometry. So what structural role does projective geometry play in helping students understand hyperbolic space?
Yeah, that is the most difficult to digest for me also. So projective geometry comes up naturally, very as geometry was used to make perspective drawings. There it was necessary for the painters to understand projective geometry. In other words, to get from a three-dimensional world to a two-dimensional world, one needs projective geometry first. And therefore, also in the axioms of Hilbert, the three dimensions are introduced if one wants to have also to deal with Euclidean geometry and the projective geometry. Then the uniqueness parallel is not questions in that part. One assumes that. But one has the certain properties which are evident if one uses three dimensions and which get really not self-evident in two dimensions. That is the so-called theorem of Desargues. And that is really only in the sixth volume that I talk about this. Here you see the picture from the theorem of Desargues. That's a bit complicated picture. You have two triangles, and if you look at the picture, you don't know is it two or three dimensional.
Right, yes.
If you interpret it as three dimensional, then this is a three-side pyramid which is intersecting with two planes, which makes the two triangles out by cutting into this pyramid. And then you see those two planes can intersect on one line. Yeah. And also you can see that if you extend the sides of the two triangles, then you get points of this line. So that is a natural three-dimensional interpretation of this figure. But if one has not the three dimension, then this figure has a peculiarity which is not evident. You have these two triangles which have the property, if you connect the vertices pairwise, the three intersect in one point. The three vertex pairs intersect in one point, the tip of this pyramid. And if you extend the sides of the triangles, you get three intersection points, and the three intersection points lie on one line. Yeah, this line down there.
Yes.
Yeah, and
Yes.
one of the two assumptions of these two triangles would now imply the other one, and vice versa. That is not following directly from the axioms of incidence, like Hilbert puts it in his axiomatic geometry. It is an additional property of just points and lines. And that's the so-called theorem of this arc then.
Okay.
And if one goes to coordinate geometry, it turns out, and that was really kind of the beginning of this Hilbert writing on geometry, if one puts the theorem of this arc in coordinates, then it corresponds to the fact that there are certain laws of algebra, the associative law of algebra for the numbers which give the coordinates. So that is already a quite astonishing connection between geometry and algebra once one uses the coordinate plane. That was not so evident, and that is one of the things which is investigated in detail in the Foundations of Geometry of Hilbert. And there, you see, you can only understand really the laws of perspective is also you use some measurements of length, not only just in the theory of this arc. You need somehow to talk about of the measurements of length, how they appear in the three-dimensional world and in the two-dimensional world depicted. And there, if you want to relate this, you need to introduce measurement into the projective geometry. Yeah. And then you can find from what you see in a photograph the real lines and such problems.
Okay. So, which geometric phenomena truly required computational visualization? So, what deeper insights did technology make possible that traditional straight edge and compass diagrams could not?
Yeah, as you see, straight edge and compass use the Euclidean geometry and make sense in the Euclidean geometry. And they are used by Euclid more than by Hilbert. Euclid likes to use straight lines and circles from the beginning. Therefore, it is more really like a mixture of childlike and architecture's view of geometry, which begins in Hilbert. And with this mixture, you get to easily to Thales' theorem, for example, of the right angle in the semicircle. Yeah, there you need straight lines and circles both for this figure. If you make the axioms of Hilbert, he ignores totally that there is something like a circle or even like a compass or even like a circle for a long time. That makes it a bit dry, yeah? And the reason why he does this, I can only guess it is because he's in the beginning more interested in the perspective and the problems of projective geometry, where circles are not of the primary concern. But in Euclidean geometry, circles are quite important, and sooner or later one needs to introduce them also. Yeah. And if one wants to do this, one gets into some additional work to work also with circles, at first without the parallel axiom and then with the parallel axiom. And that I did in my oeuvre quite in detail. I deal with circles, what you can do with them just in neutral geometry, and then with circles what you can do in Euclidean geometry. And there comes the natural problem that with a compass you draw a circle and you want now to go to another point for the other new midpoint and draw a circle of the same radius. Yeah. How can you do this? Do you need the parallel action to do this? Do you need the principle of superposition, or can you do it just from Hilbert's actions? These are questions about which I pondered more and which I have detailed more. And yes, you can do it, but it's a bit strange. Yeah, that you don't need even the parallel action to transport a circle and keep the opening of the circle and transport a circle from one place to another. That is one thing which is usually overseen in the traditional books, but I have done this in detail.
Okay. So, on another note, let's talk about your coverage spans neutral geometry, Euclidean refinement, projective structures, and a full hyperbolic treatise. So, how did you balance strict formal proof with the intuitive development needed when students first confront curvature, the failure of the parallel postulate, and metric deformation?
Yeah, how to make such a whole treatise which wants to get some nearness, some contact and exchange with students, and nevertheless understand the logical trickery which I have now tried to explain already very much. I could not explain in any school lecture what I have explained for the last 15 minutes so quickly. Yeah. Then the only way out is, yeah, or there are two components of this perhaps. One thing is one needs to pose problems which let students think about what one is talking about. Yeah. For example, you have now this construction axioms from Hilbert, and you want to erect an isosceles triangle on a segment. How can you do this? Yeah. And then pose some problems related to this. If you have a line and a point, how can you construct at least one parallel? And there are different ways, but then these are constructions which you can do and problems which you can solve. Yeah. And the other part of dealing with students is, well, if they come up with totally different ideas, sometimes it works, very seldom, but sometimes it does happen. And otherwise one needs to say, no, I'm the teacher and I say now this doesn't work and we can try this and this. And I say now for this lecture, I want still not to assume the parallel axiom or something like that. Or for this lecture, I want not to assume that a compass can be transported from one place to another without altering the opening or something like that. Yeah. So one is in the teacher in the conflict to make it easy and manageable and to also hold up the rigor which is necessary for such a topic. Yeah.
Okay. So, your final section discusses Gauss's work on curved surfaces and the pseudosphere. Do modern students fully grasp the philosophical shift Gauss introduced that geometry could describe intrinsic curvature independent of ambient space, or does that moment remain historically difficult to internalize?
You mean the idea of curvature is what you want to have explained?
Yes, yes.
That idea does not come up in that work of geometry only at the very end. Even if you draw a circle, you have basically two ways to approach it. You can begin with the middle point and all points with the same distance from it, or you can go along the line. Always go a small distance along the line, then turn by a given angle, go the same distance, turn by the same angle, and go on like this. But do this with a very, very small distance, and you get also a circle. But it is not quite clear that in the second way, even your line will be a circle. And in the hyperbolic world, if the curvature is too small, it will not be a circle, but it will be a curved line which goes to two different points in infinity, or even to the same point at a very infinite line. That was along the ideas which Lobachevsky found the hyperbolic geometry, beginning with these ideas. And then you can begin with these ideas and then go how they are related to the possibility that they are unique parallels or not unique parallels. Yeah, these are the ideas of Lobachevsky, a bit at least. They are not studied in detail in this book because I prefer to build hyperbolic geometry on Poincaré's model. And then what I said is quite obvious. You have the very large disk with the edge of which can never approach because the distance gets smaller there measured. And then if you go with a constant curvature, then you get in this model a circle which either is totally inside this disk or a circle which intersects these lines of infinity. Yeah. And then it's obvious that there are these two kinds of circles. Yeah. So you see, with Poincaré's model, some ideas get simpler, as if one wants to ponder them just from scratch, as Lobachevsky did. Yeah.
Okay. So let's talk about Fermat polygons. Okay. So your reflections on Fermat polygons highlight a rich intersection between geometry and algebra. So what led you to emphasize them as a teaching tool, and how do they help students internalize the algebraic structures underlying classical number theory?
Well, I did not always in my course talk about the theorem of Des Arcs. There's also a related theorem of Pascal, which are very close related to the algebraic properties of the field which makes the coordinates. That part of projective geometry is a bit difficult to explain to students. I put it in my sixth volume there about projective geometry. There I deal with Pascal's and with Des Arcs theorem and their relation in detail. But that I usually did not do in the basic fundamental course of geometry.
So you have created competition problems for mathematically gifted students. Which
Yeah.
types? Diophantine problems, modular arithmetic, group theory, or combinatorial number theory best reveal genuine mathematical maturity? Did any evolve directly into the sections of your book?
Yes. These problems were more on the topic of algebra than of geometry, and I had one student for a long time who liked to deal on problems, and there's especially the problem of the sum of two squares and which primes are sum of two squares and which not, and which numbers one can get by sums of two squares and which one cannot. And these problems are dealt with in detail and included in my book, which I wrote on essays of modern algebra. There you can find a large section on the sum of two squares, for example, the sum of two squares problem and how it can be solved and how it's related to complex numbers and how it's related to make a plane where the coordinates are not integers, but integers modular number. And then in that coordinate plane, you can also do some simple geometry about areas of squares and so on. And then you can find out about this fact, whether there are square whether the prime number is sum of two squares or not. And these were algebra problems, and some of them lead to some working with students and explaining things and letting them do problems, and other turn out to be not so suitable. It is kind of weird a bit. Also, I dealt with the problem how to calculate pi if one uses the arctan series. The arctan of x is x plus x3 over 3, x5 over 5, x7 over 7, and so on. And if one wants to calculate arctan 1, which is pi over 4 this way, then the series does not converge nightly. But one needs to do some trick with the addition of arctans. And I also worked on this. The simplest formula is about arctan 1/3 plus arctan 1/2 here, which gives also a simple formula for pi. Some of this, what can be done in that sense, is also in that book here. So some of the problems then led me to write myself some interesting things. And that problems are really liked by students, that happens also, but it mostly leads to be simpler problems.
Okay, so let's talk about the Lisp and structural thinking. So your adoption of Dr. Rocket, Lisp-based, is especially intriguing. So how did functional programming influence your thinking about number theoretic algorithms? Did recursion and symbolic manipulation reveal patterns less visible through traditional proof methods?
Good that you ask about that. So the programming, I did try to incorporate some programming into my teaching as I was visiting Ludwigsburg in Germany. There they were fond of that, and I learned Lisp and but not Mathematica yet a bit, and we programmed things like drawing the field for the game Halma or something like that with two triangles and some points and inside this. But then I gave up to do this with students and learned Mathematica, which is based made by Wolfram, the teaching assistant of nobody else than Richard Feynman. And he he invented Mathematica, which is really based on the ideas of Lisp. And in the beginning, I found this difficult, but then I really liked it more and more. And there I worked on the problem to construct the regular 17 gon. Yeah, going back to Euler. No, to Gauss, really. Yeah, and there is a method also to construct the regular uh, gons for the other Fermat primes. Not only the 17 gon, the 5 gon was also known in antiquity. It was more complicated, but this was known in antiquity. The 17 gon was discovered by Gauss,
Mm-hmm.
and he uses a nice order of the vertices to enumerate them, where he uses really the powers of 3 modular 17. Yeah, and the powers of then the he does not count the vertices of the 7 gon as one whole turn over 17, then 2 over times 2 over 17, 3 over 17, 4 over 17, but he counts as one whole turn times 3 to the 0 over 17, 3 to the 1 over 17, 3 to the 3 over 17, 3 to 4 over 17. That gives the counting of the edges, and then a way to successively construct the coordinates of sums of these coordinates. That was the idea of Gauss. Yeah, and I used really Wolfram Mathematica to program the corresponding thing for the other Fermat primes, not only 17. 2 larger Fermat primes. And that is written down in detail also in this book about essays about modern algebra. And that could not be done without Wolfram. And really, this was my occasion to learn and estimate really the power of computing in mathematics.
Okay, so for our last question, you describe this manuscript as a personal mathematical journey shaped by teaching, competitions, and continued growth after your retirement. So, which theorem, insight, or computational experiment surprised you most in these later years? And how did it reshape the way you framed your chapters for our new readers?
Yeah, what I will do in the future, I don't know yet. That is now interrupted more and more by the difficulties to get at least what I have done up to now to write it down more carefully. Then my effort was mainly to learn the Mathematica and to write down some of the work which is already more complete and which I have indicated a bit here and there. You can really read textbook or at least understandable and complete, logically complete in my written books. And what about this I want to do in the future? That is not yet clear. I have really concentrated on other interests in the late years. I composed music, arranged classical music, and wrote also some remembrance books, and talked about different things. Yeah, and that has kept my attention since a year or two. and therefore I'm not even up to writing a textbook in mathematics now. What I have done is writing such books, yeah. Uh, here,
Recalling
uh,
past life.
yeah, yeah, and talk about my own life and my interest in flute playing and my father and different my childhood, my father, and my flute playing together with Thomas Turner here. And I
Mhm.
talked about such things in that book and a further book I have written about that. And that keeps me busy in the moment. Yeah, and I need years, and I get slower with age, and I need to be thankful that I can still mentally work even with the bad eyes and the cancer problems I also has to take behind me, and that makes it a bit unclear about what I will work in mathematics. That is totally open. Yeah.
Okay, so can you show us the physical copies of your book, and can you say a few words to our audience about just a short line for them to like buy it? Okay, how about the geometric books?
The most important geometry book is really this volume 2 here,
Mm-hmm.
that book here, yeah. And that figure on the top here, that is really related also to the theorem of Pascal, which is there if you begin with Euclidean geometry and then make coordinate geometry from it. You need to know that the numbers which measure the segment length, that they are commutative. That is not following from itself in any way. That is some detail in geometry skipped all the time. But the proof of this is really given here in that figure here. That relates, uses parallels and angles in a circle and some things like that.
Okay, 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 that's so good. Okay, so Mr. Rote, thank you for sharing not only your scholarship but also your pedagogical vision. Your work reminds us that geometry is not merely a collection of theorems, but a living structure of ideas, rigorous, beautiful, and ever evolving. To our audience, thank you for joining us at Bookwrights House. We hope this conversation inspires you to see geometry not only as a discipline of lines and actions, but as a profound exploration of structure, space, and the thought itself. So until next time, keep reading, keep questioning, and keep discovering. Okay.
Yeah, thank you so much for your help. Yeah,
Thank
yeah.
you so